Welcome to episode 22, Picking the Right Data Store on GCP, where we explore how to choose the best storage option for a given workload. The Google Cloud Platform offers multiple database and storage technologies, each designed for a particular balance of performance, structure, and scalability. The challenge is not learning every product name, but understanding what kind of workload each is meant to serve. Choosing correctly can make systems simpler, faster, and cheaper to operate. Choosing poorly can cause bottlenecks, consistency issues, or unnecessary cost. In this episode, we will look at how to match data characteristics such as read and write patterns, structure, and latency to the right storage type so that your architecture supports your business goals efficiently and reliably. The first step in selecting a data store is identifying how your application reads, writes, and retrieves information. Some workloads involve constant small writes, like logging transactions or sensor readings. Others require fast, complex reads, such as dashboards pulling aggregated data. Latency, the delay between request and response, often determines whether a store can support the workload's performance requirements. For example, a stock trading application cannot tolerate long delays between updates, while an archive of video footage can. Understanding these patterns prevents over-engineering. You can choose low-latency databases where speed is vital and simpler, lower-cost stores where access is infrequent. Every decision begins by asking how the system will interact with its data in real-world use. A key consideration in this decision is the trade-off between strong consistency and high availability. Strong consistency means every read returns the most recent write, ensuring accuracy but sometimes delaying responses during replication. High availability favors continuous access even when updates take a moment to propagate. In a global system, you cannot have both perfectly all the time. This balance follows what computer scientists call the CAP theorem. For example, an online shopping cart may prioritize availability so users can continue browsing even if an update is pending, while a banking system must prioritize strong consistency to maintain exact balances. The right balance depends on the sensitivity of the data and the user's tolerance for delay. Analytical workloads, or OLAP for online analytical processing, have opposite characteristics. They focus on large-scale queries over aggregated data rather than individual transactions. A data warehouse is the classic environment for OLP. It must handle high concurrency, many users querying large data sets simultaneously without degrading performance. Google's analytical stores separate storage from compute, allowing elastic scaling. This means you can increase query power during peak demand and reduce cost when idle. These systems often store historical data, supporting trends and forecasting. Analytical stores turn raw information into insight, but they are not built for rapid transactional updates. Understanding this distinction prevents misalignment between tools and needs. Semi-structured and document-based workloads fit better in flexible schema databases. These stores manage data that may vary between records, such as user profiles or product catalogs. In traditional relational systems, changing columns can require complex migrations, but document stores accept evolving structures naturally. They store data in formats like JavaScript object notation, allowing each document to carry its own fields. This flexibility accelerates development when requirements are uncertain or rapidly changing. However, it also requires discipline to prevent schema drift, where different teams create inconsistent field names or formats. Document databases thrive when flexibility is balanced with governance, enough structure to maintain order without slowing innovation. Time series and wide column databases specialize in managing high-volume, time-stamped, or sparsely structured data. Time series systems excel at storing metrics, logs, or IoT sensor data, where each record is tied to a moment in time. They optimize for fast writes and queries over ranges of time, enabling real-time analysis. Wide column databases, by contrast, handle massive data sets with variable columns and are common in monitoring or personalization engines. They allow efficient retrieval of specific slices of data across millions of rows. These stores favor scalability and write performance over strict relational structure. Choosing them depends on whether your data grows continuously over time or spreads widely across categories. Caching and in-memory acceleration provide another layer of performance optimization. Rather than replacing persistent storage, they complement it by serving frequently accessed data from memory. This approach reduces latency and offloads read pressure from the main database. For example, a website might cache user session data or product pages in memory to handle surges in traffic. In-memory caches are especially useful when the same data is repeatedly requested but rarely changes. However, caching requires invalidation strategies to avoid serving outdated information. When used wisely, caching bridges the gap between long-term storage and real-time response, keeping systems responsive without over-provisioning. Object storage is ideal for large, unstructured files, images, videos, backups, and archives. It stores data as discrete objects with metadata and unique identifiers, rather than rows or columns. This makes it infinitely scalable and cost-effective for large binary content. Object storage supports features like versioning and lifecycle policies that automatically transition data to cheaper storage tiers. However, it is not suited for frequent small transactions or relational queries. For example, a video streaming platform might store raw footage in object storage while keeping user activity data in a database. Each storage type plays a role. Object storage's strength lies in durability and scale, not transactional speed. Regionality and locality influence both performance and compliance. Data stored close to users reduces latency, while regional replication improves resilience. Multi-region configurations protect against outages but can increase cost and complexity. Some data, especially personal information, must remain within certain geographic boundaries due to privacy laws. Choosing the right storage region is both a technical and legal decision. For instance, a global application may replicate data across continents for availability, but ensure that user data stays in its home country. Governance policies and architecture must align so data location supports both speed and compliance. Cost modeling connects technical design to business reality. On GCP, costs often depend on how storage and compute resources are separated and scaled. Analytical systems may charge per query or per compute node, while object storage charges per gigabyte stored and transferred. A well-chosen store balances performance and affordability. For example, hot storage might serve active workloads, while colder, archival storage holds older data inexpensively. Governance teams can use lifecycle rules to move data automatically between these tiers. Understanding cost models prevents surprises and ensures architectural choices remain financially sustainable as data volumes grow. Migration and compatibility considerations help when moving from existing databases to cloud-native options. Many applications depend on structured query language, or SQL, syntax and tools. Choosing a GCP database that maintains SQL compatibility simplifies migration and reduces retraining. However, migrating to a non-relational model may require rethinking data access patterns entirely. For instance, moving from a relational database to a document store changes how joins and relationships are handled. Governance includes planning these transitions carefully, mapping old structures to new ones while maintaining data integrity and minimizing downtime. A decision matrix can help compare options practically. Columns might include workload type, consistency needs, query frequency, scalability, and cost sensitivity. By rating each data store against these factors, patterns emerge. For instance, transactional systems align with relational databases, analytical workloads with data warehouses, and unstructured data with object storage. Document and time series stores fill specialized roles. This matrix transforms abstract concepts into actionable decisions. In practice, architects often mix multiple stores in a single solution, selecting the right tool for each data type. The key is clarity, knowing why each store was chosen and how it contributes to the overall goal. Choosing the right data store means aligning technology with outcomes. Each option on GCP serves a purpose, from structured transactions to unstructured media. There is no universal answer, only the best fit for your data's shape, speed, and sensitivity. Governance, cost, and performance must work together, not in isolation. When decisions are grounded in clear workload analysis and business context, the resulting system is faster, simpler, and more resilient. A thoughtful choice of data store sets the foundation for every application and insight that follows, ensuring the cloud works for you rather than against you. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.